Hey, welcome back to your favorite calculus class. We're going to talk about the definite integral today. And to review from last time, this was an important concept when we're finding upper and lower sums for a region. We had this function y equals x squared. You can see it here, right? Y equals x squared. And the first step was well, first of all, we were going to split this and approximate the area under the curve between the x-axis and the function into 5 rectangles or 5 subintervals. So the first thing is we found the delta x, right? Like what was this distance delta x for each of those? And I said, well, we're going to take it from 0 to 2, so b minus a. Zeros are a, b's are 2. So 2 minus 0 over 5, so we had a width of 2/5. And then to do the left-hand approximation, so from the left side, you notice we would have a lower approximation, right? We'd have these red rectangles here. Of course, there's no height on this one here. And then we said, well, let's find the formula for that, f of 2/5 I minus 1 times 2/5. We did all this, and we got 1.92. And then we did the right-hand approximation. So now we went from the right-hand side. So this would be an over approximation. And you get 3.52, right? So we had our um, with our summation notation, we could write that as f of 2i over n. So this is like our f of ci, they'll call that. And this is our delta x right there, that 2 over n, right? If we do this for n subintervals, we ended up getting this formula, right? So instead of doing it with 5 subintervals like we did over here on the left, we could do it for n subintervals, right? Obviously, if we do this more and more subintervals, the more accurate we get, as we talked about that. And then as we run the limit on that, so here's the limiting process. We run the limit as n goes to infinity on this, right? So the limit as n goes to infinity on that summation from I equal 1 to n amount of subintervals, or n rectangles, if you will, of f of 2i over n times 2 over n. Right? Again, this is like our height right here, and this is like our width right there. If we run the limit as n goes to infinity, it works down to this, and this goes to 0. That goes to 0 as we plug that infinity in, if you will, and we end up with the actual area 8/3. Right? This is called a Riemann sum. That's what this slide is talking about, where you have n subintervals f of ci times delta x or delta xi. That's just simply a Riemann sum is what we've been doing. And this limit as n goes to infinity of this summation I being 1 to n of f of ci times our delta x or delta xi, right, is the exact same thing as this right here. The limit as this is your partition, it's called, okay? So that's the width of the largest subinterval. Now we're using regular subintervals. Again, that's your partition or your delta x. It's the same thing. So as the partition goes to 0, so this is the exact same thing. The limit as delta x goes to 0 of the summation I being 1 to n f of ci times your delta xi on that, or that notation right there, just so you see that. Well, guess what? These are equivalent because if your, let me go back to this for a minute. If your delta x is going to 0, right? If this space is going down to 0 because you're getting more and more subintervals of this thing, that's the same as the number of subintervals going to infinity, right? So these are equivalent. And this is your definite integral. This is from a to b of f of x dx. That's the equivalent to that. So we're going to be able to shortcut this process. Instead of running a limiting process and doing these Riemann sums all the time, we can just take an integral. And more specifically, this is called a definite integral. Now we haven't gotten to the fundamental theorem of calculus officially, but I'm going to go ahead and give it to you so that we can use this as well. as we're talking through the geometric and the limiting approaches to these things. So the fundamental theorem of calculus, and some textbooks will call that fundamental theorem of calculus part 2. This just says the definite integral from a to b of the function f of x dx is equivalent to the antiderivative. So you get the antiderivative and then you evaluate it from a to b. In other words, you plug the b in, subtract, you plug the a in, and this gives you your definite integral. Okay. So this is just showing you parts of the definite integral. You got your lower limit, you got your upper limit, your function, you got your variable of integration that you're taking right there with respect to x there. If you are able to run the integral, you must have continuity because continuity implies integrability. So if it's continuous, then you can take the integral. So let's talk about this function for a minute. From -2 to 1 of this function 2x. Now before, what we did is we found the delta x, right? So we found the width, found the equation for our height. We ran this limiting process on this thing, right? The limit is the delta x goes to 0, which is the same thing as the number of subintervals goes to infinity of the summation of f of ci delta x. And we run through this and we end up getting a -3. Okay? And obviously a lot of work, right? This is what we were working on last time. Well, now we can just run the limit and take the definite integral. So let's run the limit of 2x. So 2x to the 2 over 2. Remember, go up 1. So it's x squared, and it's from -2 to 1. So here's our antiderivative. Our integral is x squared. Now we plug the 1 in, and then we plug in the -2. And we subtract the 2. So 1 minus -2 squared is 4. 1 minus 4 is -3. See how much easier that is? Now we don't have to run through this limiting process every time. Okay? Of course we can. Now let's talk about this definite integral. Notice this function y equals 2x right here. And we're going from -2 up to 1, right? Well, this part here, when we're taking these, when we're running through this limit and infinity summation I equals 1 and f of ci times delta x. When we're finding the function height, right, like right here, this is a negative value because we're plugging in, let's say we were doing left-hand side or whatever, we're finding the height right here. Well, it's a negative value, right? 2 times whatever it is, -2, right? We got -4. -4 times whatever the width is, depending. But this is negative, and this is positive. And then you're adding up all these negative values, right? So this is all negative. So this part's negative, and of course this part's positive because your heights up here are all positive, right? The y values there. So this is not representing the area of the region. It's not representing the area of the region. Okay. You have to be positive to be representing the area under the curve. So from A to B, you're finding the area under the curve right there. Again, that's because you're positive. Okay, so you got to be positive. If you're not, okay, like let's say you're doing something down here. Let's say you're doing the integral from 0 to 2 of this function, whatever this function is. Let's say it ends up being -3. It's really representing the opposite of it because it's summing up all these rectangles that have a negative height, if you will, because it's taking the functional value times the positive width and it's adding them all up. So the area would simply be the absolute value if it's negative. Okay? So we can evaluate the integral in actually more than a couple of ways. We can run the limiting process. We can also think about it geometrically if it's like a rectangle, a triangle, a semicircle, or something. And then we can use that fundamental theorem of calculus. And we're going to examine it in all those ways today. Okay, so we're going to do these ones geometrically, and I want to show you the first two with the fundamental theorem of calculus as well. So let's look at the first one. We have the function there is y equals 4. Right? So 4, there's our function. Here's y equals 4. From an x value of 1 to an x value of 3. So this integral is saying, hey, what's this area, right? What's this area? This is y equals 4. So the area, we know geometrically speaking, if we're solving this, we're like, oh, that's just a rectangle. Area is length times width, or base times height. So our base here is 2, our length here is 2, our height here is 4. So we've got an area of 4. Now, if we were doing that with the integral, using the fundamental theorem of calculus, we say, well, from 1 to 3, and this does represent area, it's all positive here, 1 to 3 of 4 dx. So the constant stays there, tack on that x, go from 1 to 3. This becomes, now we plug the 3 in for x, plug the 1 in for x. So we got 12 minus 4, which ends up being 8 on that. Okay, let me erase this now. And let's do this next one. So now we're going to do y equals x plus 2. Let's draw that. From 0 to 3. Okay, here's our function going from 0 to 3, right? So we're like, hey, we're trying to find this area. Okay. So you could do this one of a couple different ways. You could say, well, this is a trapezoid. If you remember, the area of a trapezoid is base 1, base 2. If this is our height, the area is 1/2 h base 1 plus base 2. Okay. Here's our base 1, here's our base 2, and this point right here is 3, 5. So this is a base of 5. This is 0.02, so that's 2. Our height right here is 3. So this area geometrically is 3/2 times 7, so 21/2. If we're doing this with the fundamental theorem of calculus now, run the integral, so x squared over 2 plus 2x, plug the 3 in, so we got 3 squared over 2 plus 2 times 3 minus, now we throw the 0 in, 0 squared over 2 plus 2 times 0. Well, both of those are gone, so we got 9 over 2 plus 6, 9 over 2 plus 6, or 21 over 2. Okay. All right, this last one, negative 2 to 2, the square root of 4 minus x squared. Erase this, sorry. All right, so if we draw this one now, we've got from negative 2 to 2, finding this area. Well, this is, if you were to write this, square both sides, right? Like this is our function. y squared equals 4 minus x squared. I'm just trying to get you to recognize that, oh yeah, this is a circle with a radius of 2, right? X squared plus y squared equals 2 squared, r squared. But it's just the top half, right? It's just the top, the square root. It's not, because if you were to solve this back down, you'd get plus or minus. It's not the bottom part, right? We're just doing the top part. Okay, so we'll just find the area under the curve. Well, what's the area of a circle? Pi r squared. So it's just half of that. 1/2 pi, radius in this case, 2 squared. So we got 2 pi. Now, the definite integral on this one, we're not going to do this for quite a while in your calculus course. It's a really big mess, so we're not going to deal with that right now. Here's just the looks at those. Okay, solutions there. Now, the definition of the definite integral is specifying that a is less than b. But let's think about here a couple different properties here. What if you just have it going from a to a? Like you have some sort of function x and you're going from 2 to 2. Well, if you think about that, if you're going from 2 to 2, you've got no width on this thing. So 0, right? You've got some height, but you got the width of 0. So the area under the curve, 0. Now, what if you were to switch this around? We know from a to b, f of x dx, per the fundamental theorem of calculus, is f of b minus f of a. So what if we did, um, how could the integral be from b to a be equivalent to that, right? So if you think about how does this work here? From b to a, f of x dx, how is this equivalent to? Well, if you do the antiderivative, you get f of a minus the f of b, right? But these are not the same, so you got to throw, how are these supposed to be equivalent? You got to throw a negative in front of this thing. You got to throw a negative in front of this, which will put a negative in front of this, which makes this a positive f of b and a negative f of a, so f of b minus f of a. Okay, so in other words, from a to b, f of x dx, and this is how you'll normally see this, right? This is the opposite from b to a, f of x dx. These are equivalent. Okay, let's do some here. Oops, I forgot to blow that up. So we got the sine function again from a to a. There's no width on this thing, so this is just 0. This one, notice it's from 3 to 0, and this is just trying to get you to see the property. I can change that to go from 0 to 3. And now I can run it. So leave that negative in front. And then I go x squared over 2 plus 2x. This is from 0 to 3. Now I throw the 3 in. Oops. 3 squared over 2 plus 2 times 3 minus 0 squared over 2 plus 2 times 0. So we got 9 over 2 plus 6, or 12 over 2, which is negative 21 over 2. All right, so what about, can we divide the region into 2? So sure we can. We could go from a to c, so the integral from a to c of the function, and add it to the integral from c to b of the function. And that's the exact same thing as going from a to b of the function. Okay. That's all that this is saying there. The additive interval property, additive interval property. An example of this would be like, the absolute value of x is defined as a piecewise function. You've got y equals x on this side, you got y equals negative x on that side. So it can be split up. You can go, if you're going from -1 to 1, you'd split it up. You'd go from -1 to 0, -1 to 0 of the negative x function, right? That's y equals -x. And then you'd add in the 0 to 1 part, this part of the function y equals x dx. And then you'd run through that integral, right? You'd run through it where you take the integral of -x, so -x squared over 2, go from -1 to 0. Take this integral of x squared over 2, 0 to 1. Plug in the 0, plug in the -1. Here we get a half. Here we get a half, which of course is 1, right? All right, so more properties of definite integrals. You can put that k out front before you take the integration. You can split them up, split the integrals up, right? Plus or minus there. Here's an example if you're given some information. So we'll run it using the information first of all, so we can split these up, right? We've got pluses and minuses here. So first of all, I'm going to split this up, and I say, well, this is 1 to 3 of -x squared, but I only have what this is equal to, 1 to 3 of positive x squared. So let me put the -1 out front, and then I can make the replacement of this part, which is equivalent to 26/3. They just told us. Plus, now we're going to go, we've got the integration of 4x dx, and then we've got the integration of -3 dx. Okay, so now I have the integration from 1 to 3 of x, but not 4x. So again, I'll put that 4 out front. Integration of x dx. I know this, oops, from 1 to 3, is equal to 4. Right? They told us that. So that's 4. Then over here, it looks like we have the integral from 1 to 3 of 1. They don't put the 1 in there. Dx is 2. So what I'm going to do is I'm going to take this -3 times 1 is still -3. So I'm going to take this constant out front and have 1 dx. And then this ends up being 2. So I got -26 thirds plus 16 minus 6, -26 thirds plus 10. Same thing as 10, which is 4 thirds. So this ends up being 4 thirds. Okay. Now, if as long as f is less than g but greater than 0, in other words, is positive, then the area under the curve for f of x, right, this area value right here will always be less than or equal to the area for g. Again, that's as long as g is above f, which is above y equals 0. And that's again all that this is saying, preservation of inequality on that one. Okay. All right, finally, let's finish up with the average value from A to B. If you remember, we 2 sections ago, we talked about average value was 1 over B minus A times the area. Right? But this right here is our area. We now know that definite integral. So now the average value of the function, the average value of the function is 1 over B minus A of the integral from 0 to √3 of the function. And now we can do this. Now let's run the integral over here. So x cubed over 3 minus 1x from 0 to √3. Come up here actually. 1 over √3. And now I'm throwing √3 in for x each time. So √3 to the third over 3 minus root 3, and then minus, and now I'm throwing 0 in, 0 cubed over 3 minus 0. So I got root 3 times root 3 times root 3, which is root 27 or 3 root 3 minus root 3 minus, of course that's gone, minus 0. 1 over root 3, and then I got root 3 minus root 3, which is 0. 0 times anything, 0. So it looks like this function, x squared minus 1, the average value of this thing, it's hitting all these, hold on, let's see. Root 3 is about, let's say root 3 is about right here. Okay, we're going from 0 to root 3. So the average value, right, it's hitting all these y values, whatever they are, and its average actually ends up being 0 right there, between 0 and root 3 at least. Okay, that's what that's saying. All right, well, thanks for listening, you guys. I know kind of a longer section, but let me know if you have any questions.